¿Está apareciendo?
Yeah, so hi everyone. Welcome to this week's South American Geometry webinar session. Again, the usual announcements: if you wish to subscribe to our mailing list, you just send the word webinar to our email, following the instructions on the chat. Just the same to receive reminders via WhatsApp. You should join our announcements group by following the link provided in the chat. And just the same, you can check our calendar, future talks, as well as our previously recorded talks on the YouTube channel, again, in your chat. Today, very happy to have Professor Detang from UFF in Rio de Janeiro to tell us about the classification of full-shrinking Ricci solitons. So, Professor Zhou, you have 50 minutes and then followed up by discussion. Please go ahead.
Okay. Well, thank you very much. Thank Paulo for the invitation. So it's a great pleasure to speak about this recent work with Cheng. So as you see, the topic is a rich solid. So according to the suggestion of Paul, I should give a brief introduction of the topic. Maybe people are not familiar with this topic. So let me start with the plan of my talk. So I will compare, as the introduction, I'll compare the Ricci flow and mean curvature flow and some classical flows. So after that, I will say some examples of self-similar solutions, and which is related to the formulation of singularities. So and then later, I will discuss briefly a monotonicity formula, which is related to the construction of shrinking Ricci solid. So at the final, I will talk about the recent result about the classification of the Ricci soliton with constant scalar curvature. So if I have time, I will give a sketch of the proof. So maybe during the presentation, I will present some open problem, which I'm interested in. So let's start. So the flow is related to some functional. For example, if you look at the derivative functional, which is the energy functional of this function, it's just the energy on the space of smooth functions. So the first derivative, I think I need to fix it something. So let me see. Okay. So the first derivative, well, the first derivative is like this. So the corresponding flow is just the classic. I have some confusions. The heat flow, right? So if you look at the area functional, we have you take a set I is the space of immersions from a compact manifold to Euclidean space. So the area function is just the area of this immersion. So the derivative of this function is just like this. The first variation formula, which we can consider the mean curvature vector as a functional, as an operator on the tangent space of this immersion. So the corresponding flow is just the mean curvature flow, as everybody knows. So if you look at another functional, which is called here the Einstein functional, so you start with a compact differential manifold. H is just a space. This is G. G is the space of all the remainder metric on M. So here with the Einstein functional is just the total scalar curvature of this metric. So where S is the scalar curvature and the volume form is just the volume form induced by the metric. So if you compute the first variation, it looks like this. So the first variation of this functional is the trace of this product. So here, the Ricci is Ricci curvature, S is scalar curvature, H is just the variation vector field. So if you look at this is a gradient, but the Ricci flow is not the same one as this. So it's just you just take a part of this. So actually, in this case, the Ricci flow is not a gradient flow of this function. So then in the first work of Hamid, he explained why he take the Ricci instead of this operator. So I will not discuss this now. So here are some examples which I put here with compare with the mean curvature flow and the Ricci flow. For example, the sphere is the example. That's the cylinder. So also you can construct the flow by the lever set of a function, which if you have a function satisfy this equation, so the lever set is just a mean curvature flow. So the Laplacian is here in Rn. Yeah, so you just Laplacian is the sum of the m plus 1 directions. You just minus this direction and plus 1 equals 0. So this, of course, there are many examples. This is quite interesting topic to study the self-shrinkers, translated solitons, and self-expanders, which is not at the topic of today, but I just want to compare with Ricci flows. So if you take the sphere, I forgot to put T here. So no, not T. So if you look at this flow, the sphere, the movement by this one, this is a special solution of Ricci flow. Of course, we also have the cylinder. You just compare here, the radius is different from the mean curvature flow ones. Mean curvature flow ones, you have the dimension here. So that means you don't have n cannot be 1. So S1 is not a special solution. So you also have cylinders, the same reason of this one. Hamilton constructed the translated soliton, state soliton, which is called SGRS solitons. Also, all the rotational symmetric soliton was solved by Robert Bryant, which now we call Bryant solitons. So the solitons, shrink solitons is related to the type 1 singularity of the Ricci flow, which means for the singularity, which means that if you have a solution of Ricci flow on the maximum interval, so the maximum interval implies that the slope of the norm of the curvature tensor goes to infinite. So in this case, you have two possibilities. One is the slope of the t minus t, the norm of the curvature tensor. This one is finite when t goes to the maximum time. Otherwise, we call it type 2. So the two types of singularities requires the different scaling of the Ricci flow. So today I will talk about the type 1. So to say this one, we need to see a monotonicity, which is quite important for the study of the Ricci flow. So to do this, we just look at the classical case, which is heat flow, which is done by Becker-Emery. So this is just a heat flow. Yeah. So you have a solution which satisfies this heat equation. So it's not difficult to see that only this part is decreasing, but the Becker-Emery put an additional term here, which is log term. So they proved that this one also has monotonicity. In particular, it can recover the logarithmic equality. This I think it motivated the Huisken to find obtain another monotonicity for mean curvature flow. Look at this one, the mean curvature flow. You can put this one as Laplacian xt, so which is similar to the heat flow. So he proves that this one also less than or equals 0, but here h is not exactly the heat kernel, because now it's the manifold has dimension n, so h flow it is similar, but it's not the same one. So they have this monotonicity. That is quite surprising. In particular, if you take a variation formula, it can produce the self-shrinkers. So it motivated the Caudy-Mini-Cos defined this function, F function, and using this, defined this entropy. Using this, Caudy-Mini-Cos can classify the generic singularities for mean curvature flow. The idea is important that, in the sense that when you want to study the singularity, of course, if you can classify all the singularities, it's okay. But usually it's very difficult to classify all the singularities. But from the mean curvature flow case, maybe you don't need to classify all the ones. You only need to classify the stable ones. If the stability is related to the entropy. So if the singularity is not stable, that means there is a direction you can deform it such that the entropy goes down, and if you continue the flow after the perturbation, then the flow will not come back to that singularity. So you can use this idea to remove the singularities along the mean curvature flow. But it is interesting that the Perelman defined as a similar entropy, which is come from the W function. It's like this. So you have a manifold, fix the manifold. You have metric, you have a function, you have a number, positive number. So the W functional is defined as this one. In the first side is quite complicated. If you isolate this term is just a measure, probability measure. So here you have S is scalar curvature. The gradient F is the gradient F of this one, related to this metric. So you have the F minus N. So on compacted Riemann manifolds, the Perelman defines this entropy, this functional. Okay. So later he defined Perelman compute the first variation of this functional. So now you have three things: G, F, and tau. So you take this one, H is H and phi and at. So the first variation is quite complicated here. So here you can see there's H here. This is respect to metric. The second one is respect to phi. So you have here, you have here is the phi is hiding here. So the third term is the number. So here you have d phi is here, and the first derivative of the measure is here. So the phi comes here. So it is not isolated. So you have two terms here. Anyway, if you look at this one, for example, if you fix, if you assume this one is 0, and you can assume this one is 0, so you only have this term. So the critical point for the metric with the F, so if this one is 0 for all H, that means this one is 0. Right? So that functional, it's not, as we said, that the Ricci flow is not the gradient of the Hilbert functional. So this functional can give the monotonicity for Ricci flow. So the Perelman, instead of using Ricci flow, he considered the coupled modified Ricci flow. So that means you take add an additional term here. It was only for metric. Now he increases a space of function and increase a rescaling factor. Then he can prove that that functional. Actually, I wanted to explain why he constructed a double functional. So the functional has monotonicity, right? This one. So along that flow, you have this, and you can see this one that the equality holds. That means this one is always bigger than or equal to 0. The equality holds if and only if this one holds, which we call shrinking gradient rich solid. So that means that shrink gradient rich soliton is just a critical point of doubly functional. That is why you have function, you have number here. Perelman also defined the new energy, which we call new energy. If you fix a metric, you take the infimum of W on the space for any function and the tau positive. Then this number is also non-decreasing along rich flows. If you have any question, you can put somewhere. So it also makes sense you just take an infimum for functions, just fix the u here, the tau here. So this functional, the critical point of the Euler-Lagrange equation for this function for f is just like this. That means if you want to find the infimum, you just need to solve this equation. It is interesting that using this concept, so a pair of metric and a number is of a Riemannian metric and a number which is called regular if there is a neighborhood u of this metric and an interval of tau such that the metric, any metric and tau, the minimizer is unique and depend on the g and the tau analytically. So the sum and one proves that any compact gradient rich soliton is regular. That means the infimum, this number is can be achieved in the neighborhood of a rich soliton. So it works for the study of singularity. Now we can see some properties of this equation. So we can normalize. Let's go back to this equation here. If you look at this one, we can normalize this constant such that tau is 1. So this is the equation with respect to metric and function f. So if you like, you can write it on Rn. So the Rn is just a hashing of this one, which is a Gaussian solid. In Rn, Ricci curvature is 0. The hashing, if the hashing is parallel to the metric, you can solve it. F is x squared over 4. So later we will see some examples. So there are some basic properties. The first one is Hamilton proved that f can be normalized such that the scalar curvature plus the gradient f, the norm of gradient f squared is equal to f. And Cheng proved that this Ricci shrink gradient Ricci soliton always have scalar curvature non-negative. So equal, and furthermore, it is proved by several people that S equal to, if you have a point, scalar curvature is 0, then it must be Gaussian solid. It must be flat. Also, Zhou and I proved that for any complete non-compact gradient rich soliton, we can prove that the function is just, the potential function is just similar to the Gaussian soliton. The important thing is that you have the same constant here. And then it's also important we don't need any curvature conditions. Actually, this kind of results was proved by Perelman when he assumed that the curvature is non-negative and bounded, and with this one is 1/8, the Perelman. But it seems that we don't need any condition. We can put 1/4 here. That means that if you take twice of this one, f, this function is similar to distant function r, where r is a distant function. So when you're on a rich soliton, shrink soliton, you have a natural function which is similar to distant function. Of course, distant function is not always smooth, but this function is smooth. So in many cases, you can just use the potential function instead of use the distant function to get some estimate. Okay. So we also proved that the volume of the geodesic ball has some growth at most at the Euclidean space, which is similar to the complete Riemannian manifold with non-negative Ricci curvature. We have this term. I just want to say a few words about the singularity, type 1 singularity, and the shrink-rich soliton. In 2010, Aders, Müller, and Topping proved that if you have a type 1 rich flow on this interval, maximum interval, so if you take a point of the near singularity, then for any sequence, you just take a rescaling of the rich flow. Remember that the rich flow is parabolically scaling invariant. So you just take this time, you take divided by this time, and lambda j goes to infinite. So that means you make flow slow, and on the other hand, you just make the metric bigger. So you have a metric which depends on t. So this is a new flow. This also satisfies the this one Gj is also rich flow. Then this rich flow subconverge to a normalized, non-trivial gradient shrink rich soliton. Right? That means almost every type 1 rich flow, type 1 singularity for rich flow will produce a gradient shrinking soliton. So of course there are several questions related to this theorem, because he said the subconverge. So there is a natural question: is the limit unique? Of course, if you can classify all the soliton and shrink soliton, this must be unique. The unique means that if you take another sequence of lambda j, so that means you have the same limit or not. So this is an important question for the surgery of rich flow. Right. Also, we have we know that the positive Ricci curvature is preserved by rich flow in 3-dimensional case. That means you only have type 1 singularity, which is proved by Hamilton. If you assume the positive Ricci condition. So the Ricci condition, the curvature condition preserved by Ricci flow is a very interesting thing. I just mentioned some result here several years ago. For example, the positive curvature operator condition is preserved by Ricci flow. So that also means that you only have type 1 singularity, which was proved by Hamilton, 4-dimensional case. And it was a Hamilton conjecture for any dimension, which was solved by Born-Wicken. Another condition from the peak called peak. Peak means positive isotropic curvature condition, which is preserved by Ricci flow also. That also you have type 1 singularity. This implies that the quarter pinched condition is how to say that quarter pinch is a part of the metric with peak. So using this one, they proved that the quarter pinched differential sphere theorem, which was done by Brenner and Schoen in 2006. Of course, it remains open there if you can find some another conditions which is preserved by Ricci flow. Also, there is an interesting thing for the shrink Ricci soliton. So as we see that this is the most famous shrink Ricci soliton, which is Gaussian. We just take the canonical metric and take a potential function like this. Then you have Ricci. Actually, you have Ricci one. Ricci F is this. So anyway, on any Ricci soliton, you have this one for the top. Yeah. So you can compute the entropy of this Gaussian soliton is just 0. There is a gap theorem done by Yokota. Yokota did it for he proved that if you compute the weighted volume, which is like this, so that means this is 0. It's equivalent to this weighted volume is 1. So he proved that there is a constant only depend on n, such that this one bigger than 1 minus epsilon n, then it must be shrink solid. I need to be a little bit quick. So I think I need to skip this one. Of course, I wanted to explain the entropy stability, but anyway, I think I don't have time. I want to go further. So there are some, just to say a few words, there are some similar entropies with mean curvature flow, which is important for the stability, for the surgery of mean curvature flow. So there are several questions. The most interesting question here I want to mention is that of course, we want to classify all the string solitons. So there are several questions. For example, can we classify all granular Ricci solitons with constant scalar curvature? Also, if we want to classify all the Ricci shrink solitons, of course, we need to classify all shrink Ricci solitons. So if you cannot classify this one, can you classify the shrink ones with constant scalar curvature? Also, we can say that there is an important problem that you can, if you start with is related to Hopf conjecture. If you start with the Hopf conjecture asks that S2 cross S2 has positive sectional curvature or not. The natural way is that if you assume there is a positive curvature metric on S2 cross S2, so you need to know this. If you put it in Ricci flow, you need to what happens the first singularity. So of course, we are interested to classify the four-dimensional case, classify the ordered shrink-rich solid. So there are to compare with the no-dimensional case, there are several results here for the classification. The first one is the Hamilton classified ordered two-dimensional case, shrink-rich soliton. He proved that it's either isometric to plane or a quotient of sphere. And later, for three-dimensional case, there are a lot of works until 2008. First, Ivory, Perelman, Labor, and Lee Wallach. But finally, together with all the works, Huaidong Cao, Binong Cheng, and Xiping Zhu proved that this is a joint, a collection of the works. All the three-dimensional gradient shrink-rich soliton is there are some mistake with the PDF here. Or round sphere is the quotient of or round sphere or the quotient of Gaussian-rich soliton or the round cylinder, the quotient of round cylinder. Also, that means they have classification of all the gradient-rich soliton in three-dimensional case. I didn't check it. I don't know why this PDF is different from the one I put. So later, the Peterson and Wiley defined a gradient-rich the concept, which is called rigid. This said that the, I don't know if I can do it. So he generalized this fact to any dimensional case, which is called if you have a gradient-rich soliton is rigid if it is a quotient of a product of Einstein manifold with Euclidean space. That means rigid. In this case, all the rigid ones has constant scalar curvature. I think I need to do something with the PDF here. Sorry for this one. Okay, I need to reopen it. There are some problems. Okay, Is this too small?
That's good. I think that's good.
There was some problem that there was some collapsing with it, so I need to. Okay. It was an accident. Okay, here. Now it's okay. The rigid one. So it's natural to ask, in four-dimensional case, all the gradient shrinks rich solitons should be rigid or not? Because in two and three-dimensional case, you don't have examples with a non-constant scalar curvature. And actually, the four-dimensional case is really different. So it was constructed by Koizu and Huaidong Cao. They have in four-dimensional case the shrink gradient rich soliton has non-constant scalar curvature. Right. So in any dimension, the Eminetti, Lalave, and Montichese prove that the compact rich soliton is rigid if and only if the scalar curvature is constant. So after that, there are another work to work on the four-dimensional case, and for example, the labor showed that a non-flat, completed, non-compact gradient-rich soliton, if we have the curvature tensor, a curvature operator is non-active and bounded, then it has to be this one, and in the quotient of this one. And also, the Peterson and Wiley, they proved that for any dimension, if you have a constant scalar curvature, and with this condition, it's called a radial flat, or the sectional curvature, which contains the gradient f has to be 0. So then they prove that the scalar curvature is rigid if and only if if the scalar curvature is 0 or n lambda. In this case, the lambda is 1/2. Down. So if and only if the underlying metric is Einstein. So they prove that if the scalar curvature is constant and equals to 0 or this number, then it has to be Einstein. And later, Fernandez Lopez and Garcia-Hill, they proved that if the scalar curvature is constant, the positive value of the scalar curvature is just this table. The lambda is, you can consider lambda is as 1/2 here. So only have these possibilities. And furthermore, they prove that if the S, you can see here, the Peterson and Wiley proved this one and this one. And this one, the Fernandez and Garcia-Hill proved that this one and this one cannot happen. If it's not, or can happen if happen, this one cannot happen. This one, if it happens, then it has to be rigid. So, so that if you look at the four-dimensional case, for example, the only remaining case is that if you look at the four-dimensional case, only case is that scalar curvature equals to 2 lambda. That means if lambda is 1/2, that means S is 1. So in this case, they tried to prove the same result, but they can only prove that it has non-negative Ricci curvature. So that means in four-dimensional case, you have 0, 2 lambda, 3 lambda, 4 lambda. You have this one has been proved, and this one, they proved that must be this case. So this one is the only the unique unknown case. Fortunately, we can prove that actually we can classify this one. If you have a four-dimensional complete non-compact grand Ricci soliton, satisfy this one. If the scalar curvature is equals to this one, then it must be S2 cross R2 or finite quotient of them. The proof is quite different. We need to work a little bit to compute the order things here. So I will skip this one. Actually, I prepared a list of references here. We try to work with Y tensor. There are many works here. So I just want to show that there is a long list here. So using the Y tensor, because of four-dimensional case is a very special case. So many people are interested in this one. So the first they assume that Y tensor is 0. They can classify it, and then later they say that you don't need to compute the Y tensor. You only need to one of this Y tensor 0. They can prove. And then later, Xiaodong-Cao and Cheng prove that you don't need that this one equals 0. You only need to assume this one 0. And Huaidong-Cao and Cheng proved that using Baha flat also has this one. You can see all these examples don't have S2 cross R2. Yeah, it has this one. So people are working towards the S2 cross R2. So here is there a list of works. They prove that if the Y tensor is harmonic, they can prove that now you have this example. That means W is not 0 on this example, but W is harmonic. An interesting result is that the Kim proved that the condition of local harmonicity of Y tensor in four-dimensional case implies that the scalar curvature is constant. If you don't assume the scalar curvature, but this one implies the scalar curvature is constant. So if you can classify all the scalar curvature constant ones, it would be nice to change the way to classify the four-dimensional Ricci solid. Of course, there are some global results I just mentioned here. In one word, the four-dimensional case is quite attracting dimension. So let me say a few words about the proof. In the proof, we will use some basic properties I just mentioned before. we will need a list of the formulas about the curvatures, which has been used for by many people. The one thing which was not very easy to use is this one. So it's not very pleasant to see, but when S is constant, you have a equation here. So this is one of the key points in our proof. So to start with the proof, we need to study the level set of the potential function. Actually, if the scalar curvature is constant, you have the function f is isoparametric. So since it is isoparametric, you can using the theory of isoparametric functions, which, for example, in this case, we have proved that the function goes to infinite. So you only have one focal point, one focal manifold, which is connected and minimal. And you can write down the potential function with the distance function of between the focal manifold. Also, you can characterize the level set of the potential function. The level set of the potential function has dimension 3. See, so one thing if dimension is 3, you can write down the curvature tensor by Ricci tensor. So the idea is that we using the potential function, and we can, in dimension 4 case, we can decompose the Ricci tensor by Gaussian equation, which is related to the Ricci curvature tensor on the level set and the one direction of the gradient f. So so we can normalize as net s equals to 1. So when s equal to 1, and let me go back to the equation. When s is constant, you have this equation. That means gradient f is the eigenvector of Ricci curvature. So when this one is 0, then you know that Ricci curvature have eigenvalue 0. So Ricci curvature has 4 eigenvalues. So you have 1 is 0. S is constant. You have the sum of the Ricci eigenvalue of the Ricci curvature is 1. So you have second equation. And when S is constant, you have this one is 0. This one is constant. So you have this one, norm of Ricci square. This one is constant. So you have 3 equations. The only one, if you want to determine the Ricci curvature, you need an additional equation. That means you need, for example, if you have now you have 1, 2, 3, you only have one eigenvalue free. So it is natural that you look at this one. So if you can prove that
we're a little bit past time. Do you think maybe we can summarize the proof in main steps?
So the first thing that I just want you to explain the idea, and then first we have s equal to 1. I want to determine the Ricci curvature, right? The main point, I want to write down the Ricci curvature. I already know the scalar curvature is 1. I want to compute the Ricci curvature has to be only have two eigenvalues, which are 1/2, 1/2, 0, 0. If I can prove this, I can everything is done, right? So I need to compute all the eigenvalues of Ricci curvature. I already have 3 equations. I need 4th equation. So that's the difficult point. The first step, I need to write down this one. The idea is that I want to compute this one. I want to find an equation for this one. I want to compute. We want to prove this one is constant. So to prove this one is constant, we need to compute this one. So this one satisfies this equation. So this is the first step. The second step, we can prove that this one has a sign, which is non-negative. So I have this one. I have an inequality. So now the difficulty is to compute this one, right? So the first, this equation is more or less direct. So to compute this one, so the most most difficult one is to estimate this one. But fortunately, using the idea to decompose the curvature using the relations above, we can prove this simple equality. It's very lucky. That means we can define this function. The main part of the computation is to prove this equality. So if you look at this function, that means you have this one. It's quite simple. So I will not, I hope that I will not have time to explain how to prove this, but from this, it's easier to explain. From this, I can prove this is constant, which is here. I just take h here, you have this equation, this equality. So using the basic result I said before, we can prove this one. That means h has to be 0. So h is 0, that means the trace of this one is 1/4. So as I said, you just have 3 equations, you have 4th equation, you can compute the eigenvalues of Ricci curvatures like this. So the rank of Ricci curvature is 2. That means you can prove this one. I think I use a lot of time. It's supposed to think 50 minutes.
Are you good?
Yeah, it's finished.
All right, let's thank the speaker, please. Okay, if people have one question, I think we could take one question, if at all. All right, Paolo, do you have a question? Does anyone have a question? Well, maybe I can ask how because what the preliminary result you showed is for just any dimension, but then you specialize to 4 dimensions when you go look into the eigenvalue problem and so on. How different would it be in higher dimensions?
High dimensions, it is possible to, for example, if you want to work with 5 dimensions, you need to compute the trace Ricci cube. You need to compute Ricci 4.
Aha. Okay.
So, but for 4 dimension, it's just very complicated because you need. We use the potential function, the level set of potential function. We write down the Ricci curvature, the curvature tensor. Avoid using Y tensor. Many people using Y tensor, but we use the curvature tensor to decompose to the curvature tensor and the F and the curvature tensor on the level set, which is dimension 3. So the dimension 3, you can write down the curvature tensor with Ricci curvature. Ricci curvature come back to the Hessian of F. So all information concentrated on the F. So level set depend on F. The curvature tensor also depend on F. So everything comes to F. So that is why we have a simple inequality. The difficulty is to concentrate it.
Okay.
Okay.
All right. Thank you. So let's thank the speaker again, please.
Thank you very much.
And we're looking forward to meeting everybody in 2 weeks' time at the same place and time for our last talk of the semester. Then I'm going to take a small break, but let's meet then for a final talk of the semester in 2 weeks' time. And as usual, you can subscribe to the mailing list by following the instructions on the chat in various different ways.